Hello everyone, I am Liang, coming from Beijing Information Science and Technology University. Today my presentation is Deny-Sensitive Slicing Results Scheduling based on Multi-MEC collaboration in IoV. This presentation is divided into these 5 parts. Firstly, I'd like to introduce the motivation of this presentation. According to Statista report, September 2021, the global market size of the Internet of Vehicles will increase from about $56 billion in 2020 to about $121 billion in 2025. For this, we can see that the strong movement for IoV continues. Vehicle to everything can make reasonable judgment on traffic information. Under automatic driving mode, minimize the traffic exit rate and realize that automatic driving is safer than manual driving. Our goal is to minimize the total cost of the vehicle to complete the computing task. We study the scenario of vehicle computing task is offloaded to RSU and consider the multi-MEC collaborative computing task to ensure that the task can be completed within the tolerable deny. We used network slicing to segment MEC service results so that multiplied RSUs can cooperate with each other in the computing task. We propose a performance-price ratio task scheduling algorithm, which aims to complete the computing task within the maximal tolerable deny and reduce the cost of user. Compared with the other 3 algorithms, PPRTS always ensures that the lowest user cost when the computing task complete within the tolerable deny. Now I will talk about the system model. In this section, we consider that in the automatic driving scenario, some vehicles are driving on the straight road, and they can communicate with RSU equipped with the MEC service through V2I link. It's assumed that there is a certain distance between RSUs, and the coverage is contiguous but not overlapping. Each RSU is equipped with MEC service, which have limited data capacity and computing power. For vehicles, they have data capacity, weak computing power, and low unit price. We use a triplet delta M D to describe the task that the vehicle needs to compute, where delta represents the complexity factor of the task, M represents the data size, and D represents maximal tolerable deny of the task. For RSUs, the computing results and data capacity of multi-MEC service are composed of network slices, which can be dynamically allocated to multiplied vehicles. When the vehicle enters the coverage M of RSU, diversified logical private network service can be realized by accessing the network slicing. In this way, there is no need to build a physical private network and avoid the actual cost and waste of results. And the compression of the network size of RSU is shown in equation 1. At time node t, we can make the coordinates of the vehicle and RSU, the channel gain and SINR between them can be calculated according to the Euclidean distance. Equation 3, 4, and 5 are the distance, channel gain, and SINR between them, respectively. According to equation 3, 4, and 5, the transmission range between them can be calculated, as shown in equation 6. The instantaneous state transmission range of vehicle is measured once in each time node, and the average transmission range is calculated as equation 7. The uplink and downlink delays of vehicle offloading are shown in the equation 8 and 9, respectively. RSU will assign the task to the next RSU, which will execute the computing task at the same time. So the task execution delay in MEC is shown in the equation 10. One part of the task is computed locally, and the task local execution delay is shown in equation 2. Thus, the total execution delay of the vehicle computing task is shown in equation 11. In order to ensure the utilization of results and the user experience, we propose that the unit price function of slicing results is equation 12. The cost of the task completely locally and offload to MEC is shown in equation 13 and 14, respectively. By integrating three models, the user's computing task cost can be defined as constraint optimization problem as equation 15, where C1 represents that the total cost assigned to vehicle and MEC service is certain. C2 represents that the computing power of the vehicle and the size of MEC service can complete the computing task. C3 represents that the maximal delay for proposing the computing task locally or MEC should not exceed maximal tolerable delay of the task. C4 and C5 ensure that the data size of the task assigned to vehicle or each slice doesn't exceed the data capacity of them. Otherwise, the task date will be not. Then is algorithm design. In this section, we solve the cost minimization problem. The first is initialization. Recording the vehicle coordinates, judging which RSU the vehicle is in, and select the RSU to offload. The next is stage 1. Selecting bins according to performance price ratio and dividing the task by data capacity of each bin. The next is stage 2. Processing the computation task and returning the computation results. In the initialization, we determined which RSU coverage the vehicles is in, and shown in encryption system. In stage 1, we regard the vehicle and NMEC service as a bin set, and we rank bin from high to low according to performance-price ratio as shown in equation 17. Now let's introduce the performance-price ratio task scheduling algorithm. In stage 1, the algorithm adopts direct performance price strategy and local priority strategy, and the better one is selected. For the task with large moments of date and high denied requirement, we adopt a local priority strategy, which makes maximal use of local computing results, and the rest part of the task is offloaded to the MEC service according to the performance price ratio. Stage 2. After formulating the task scheduling scheme, one part of the task is offloaded to MEC service for cooperative processing, and the other part is processed locally according to the vehicle speed and the task uplink and the processing deny. Vehicle coordinates are calculated. Similar to equation system, the RSU in coverage range is selected and the computation result is returned to the vehicle. Next, the simulation results show the good performance of the proposed algorithm. As shown in the figure 2, the abscissa is the computing power of the MEC survey, and the ordinal is the unit price of MEC survey results. Taking the percent fixed vehicle local price as a reference, the influence of 3 MEC survey results occupancy range on results unit price is compared. In this case, the MEC survey with no results occupancy and relatively strong computing power should be selected on the premise that the task can be completed within the tolerable delay. As shown in figure 3, the abscissa is results occupancy range calculated by MEC, and the ordinals is the unit price of MEC results. The unit price gap of each MEC service is small, before 50%, and gradually widens after 70%, which is a potential mechanism. The high cost makes the users choose the service with relatively idle results, ensuring the use experience and depressing the service pressure of operator. The total delay of different schemes is shown in figure 4 and should not exceed the maximal tolerable delay. For the experimental results, not every scheme can complete the computing task within the maximal tolerable delay. PPRTS use our proposed performance price ratio task scheduling algorithm. In Stage 2, we find that the delay of PLRRO is lower than that of PPRTS, but it is not that the lower the delay is, the cheaper the price is. It may be that the PLRRO used better computing results to complete the computing task with lower delay, but the use cost is not necessarily the lowest. Our goal is to minimize the use cost within the tolerable delay of the task. So we only need to complex the task within the tolerable delay. The use cost comparison of the 4 schemes is shown in the Fig 5. Although the cost of all window offloading is known in Sheet 3, it cannot complete the task within the tolerable delay, so it is not desirable. Realistically speaking, PLRRO gives priority to local chip computing results processing the task, so the cost is lower than the 2-window scheme. However, MEC results are relatively idle and cheap in Sheet 5, and the cost of preferentially computing tasks locally is high. PPRTS selects results according to performance-price ratio, and the use cost is always the lowest among the 4 schemes. Finally, its conclusion. In this paper, we study the cost of use computing tasks for vehicle in automatic driving scenario. In order to minimize the cost of user, we use network slicing to segment MEC service results and propose PPRTS algorithm, which offloads the computing task to multi-MEC service according to performance-price ratio of slicing results. Simulation results show that the algorithm can complete the task within the maximal tolerable delay and effectively reduce the cost of user. That's all. Thanks for your attention.